Um, Welcome everybody to the third distinguished talk on the STCS Vigyan Vidushi program 2022. We are happy to have Professor Meena Mahajan from the Institute of Mathematical Sciences, the Homi Bhabha National Institute, with us today. Professor Meena Mahajan is an expert in theoretical computer science. She started her academic career with the city of Bombay from IIT Bombay, and then went on to do her PhD from IIT Madras with Professor Kamala Kritivasan. She is an expert in the areas of computational complexity, especially her early work consisted of trying to understand the complexity of problems in the class P and even lower class P. More recently, she's been working on problems in proof complexity, something she'll be talking about in today's talk. Personally, I have known Meena for actually right from the start of my academic career. We shared an advisor. My undergraduate advisor was the same as Meena's PhD advisor. Kamala Kritivasan was also my undergraduate advisor. So in my very young start days, I heard about her thesis on cellular automata long back. I don't know if Meena recalls. We actually did meet sometime when I was in undergrad. This was long in 98 or so. Since then, I've encountered Meena several times, and actually, she's been a mentor to me in more senses of word than one since I came back, started as a young faculty in TFR over the last 10 years over here. So over the last 10 years, this one. And Meena is known to be an advisor par excellence. She's advised several graduate students who have gone on to become excellent researchers for all over the country. Currently, in the context of advisors and advisees, while coming up with this introduction, I yesterday stumbled into a curious factoid. So Meena is part of a long chain of women advisor and advisees. This one. So Meena's grand advisor is Rani Shiromani from Madras Christian College. Meena's advisor is Professor Kamala Kritivasan from IIT Madras. Meena from IMSC. One of Meena's students is Professor Nutan Lamaye from IIT Bombay and also at ITU Copenhagen. And Nutan's student is Professor Pooja Vyahari, who's a faculty in IIT Tirupati. To my knowledge, this is the longest chain of 5 women advisors and advisees I've known in theoretical computer science. I could be wrong, but I tried doing some Google search yesterday. The longest I could figure out elsewhere in the world was only 4 or so. Meena has been recognized for her work. One, she is the fellow of the Indian Academy of Sciences. She's also an ACM eminent speaker. She'll be speaking to us on complexity of formal proofs. Thanks, Meena. Yeah.
Thank you very much. So now I have this elaborate introduction and I have to live up to expectations. And I hope I do that. So here is the advertised title of my talk, The Complexity of Formal Proofs. But before I jump into formal proofs, as you have already seen when I was trying this thing, I wanted to spend just a little bit of time telling you about, how did I even get to this place where I am here as a distinguished speaker talking to you. I mean, it doesn't seem all that long ago that I would have been there, an undergrad doing computer science. And as an undergrad doing computer science, I was the only girl in my class of 24, whereas now I am in a computer science department where 3 out of 8 are women. So some changes happen over time. Right? So how did I get here? Well, as Prahlad already told you, this is my advisor Kamala Kritivasan, and that's her advisor Rani Shiromani. Advisor is at the level of PhD, but before that, I did my bachelor's and my master's in computer science and engineering at IIT Bombay. And quite frankly, at that time, I had not the least conception in my mind that I would become a scientist. IIT itself did not convey this impression of scientist. IIT was for engineering. And my undergrad, there was a lot of engineering and I did not like it that much. So it was, I kind of gravitated towards theory by elimination. Having tried out various other things, did not like them. Fortunately, I liked theory. I really loved it and stayed with it. So my PhD work was in formal languages and automata theory, and I worked with these 2 people. And while I was doing my PhD, I was exposed to computational complexity, this research area. So my colleague Arvind Professor Arvind, who's been my colleague in IMSC for several years. But at that time, he was in IIT, and he had given this lecture series on computational complexity. It was not for credit. It was not something that I was required to attend, but I did attend it, and I found it completely fascinating. In fact, I found it more fascinating than automata theory, but my advisor was working in automata theory. So it was clear that my PhD would be that. And so I tried to bring in a complexity theory kind of flavor into my PhD work. And then the moment I finished PhD, I said, okay, now I abandon automata theory and I come to complexity theory. Things change a lot over time. I mean, of course, I abandoned automata theory then, but now I find automata theory really impressive, interesting. There are lots of fascinating things happening there. And maybe if I had stuck with it, I would have done something very different. These things cannot be predicted. So yeah, like I said, I decided to move wholesale to this area of computational complexity, and I learned a lot about this field from Vinay, who was at that time faculty member at IMSC. Very briefly, we overlapped in IMSC. So I learned much of my initial launching pad complexity theory from him. Another person who has influenced me a lot, Eric Allender, a researcher at Rutgers University, and he visited IMSC a few times. We interacted a lot. So somehow the initial boost came from these people. So what is this area computational complexity about? Maybe you have some idea about it, maybe not. Certainly when I was an undergrad, I had no idea what complexity is. So I'm going to spend a little bit of time telling you what it is. Mainly the main question of interest is understanding how much resource is necessary to solve some problem. So you could be doing algorithm design. You have a specific problem and you want to solve it using only so much time, using only so much memory space, with limited resources, try to solve the problem. That would be designing an algorithm. But in complexity theory, we are turning the question on its head. We are fixing the amount of resource available and not trying to solve a specific problem, but trying to understand what are the problems that can indeed be solved within this much budget. This is the budget. Now, what is it that you can do in this budget? And more interestingly, what is it that you cannot do in this budget? So that's one of the main focus of complexity theory. So it's completely fascinating to me. It has been fascinating for a long time because you're proving lower bounds. You're trying to show that something cannot be done with less than this amount of resource. So you're trying to prove that all possible algorithms need this budget. And when I say all possible, this includes algorithms which have not even been designed. You're making arguments about completely unknown objects. So at a meta-philosophical level, this seems like an impossible thing, but of course we do these things all the time. So in my high school and college days, there were various puzzles which we used to solve. And thinking back upon that, many of these puzzles were some kind of lower bounds. How many times do you need to cut a strip in a particular way so that you get some pattern? And can you do it with fewer cuts? Well, that's a lower bound question. Okay, so since we are proving facts about unknown objects, how does one even go around doing this? Well, there are various arguments that one could use: logical reasoning, diagonalization arguments, counting arguments, adversary arguments, so on and so forth. But all these arguments so far have not given us any success so far with the central problem in computational complexity, which is the P versus NP problem. Now, again, this is a problem which some of you, I'm sure, have already heard about right in this program, but maybe not much. It doesn't matter. We are not going to spend much time on it. I just want to say that this is, like I said, one of the most important problems in the area. It's worth $1 million. Maybe at some point the 1 million may go up, but the million does not matter. Really, what matters is getting a solution to this problem. And the foundations for this formulation of this problem were laid by these people in the 70s. There had been work even before that in the 60s. Before computers were a reality, people were already talking about efficiency of algorithms. So since then, this problem has been around. It has still not been solved. What exactly is the problem? It's very informally, it could be stated as checking an alleged solution to a problem. Is this an easier task than finding a solution? And this should strike a chord with anybody who has been interacting with a particularly stubborn or harsh teacher, that you have done the work to solve the assignment. The teacher just has to correct it and can very easily say, this part is wrong, that part is wrong. A teacher can do that without even knowing the solution himself or herself. So at least in that limited aspect, I think the student's job is much harder. Okay, so this P versus NP problem, we are looking at decision problems where the answer expected is either yes or no. We're not looking at problems which require a larger output. And this class P, polynomial time, problems for which we can get the correct answer efficiently. NP, the class of problems for which at least if somebody gives you a reason why the answer is yes, you can verify that correctly, even if you don't know how to find the answer. NP complete, these are the hardest problems in NP. And here are some possible scenarios. Maybe P is equal to NP, maybe P is not equal to NP, and maybe there are more subtle things that one can say about this. So which of these scenarios is real? Like I said, we don't yet know. Why should we even care? It seems like a very abstract formulation in some sense, but it turns out that many natural problems from very real, practical, real world domains actually turn out to be equivalent to each other. They are all NP complete. You solve one, you solve them all. So then we are looking, in some sense, for the practical solutions, we are looking for algorithms which will solve the problems. We are not looking for lower bounds. So why are we interested in lower bounds? Because they tell us where we should stop looking. No, look, there's a lower bound here. You can't do better than that. Focus your energy somewhere else. So we need to set realistic expectations. Okay, we have not yet solved this big problem, but we know that the question which the reason why this question is interesting is of practical experience. Let's see what we can do. So in case you haven't seen, this is one of my favorite XKCD comics. Why is a problem which is NP complete interesting and practical? So here are these people who go to a restaurant and here are the prices, and they have a clear budget. You know, they have $15.05. So they tell the waiter, give us whatever will add up to exactly this. And this is a small enough menu that maybe you can solve it. But in general, trying to pick the right amount of each item so that you get as close to your budget as possible is a computationally hard task. Think of a file with thousands of items like this in a database, and then you're trying to optimize. We don't know how to do this efficiently. So this is like I said, one of my favorite XKCD comics, but here's another favorite, the traveling salesman problem, where somebody just has to go across to various cities and is trying to minimize the cost of traveling all around. And again, we do not know how to find an efficient solution. Yeah? So you see this, the frustration in the last slide. But fortunately, we who are working in complexity theory are not yet frustrated. We are making progress in slow, small steps, and eventually we will get to what we want. Okay, so like I said, P versus NP, it's the central problem in computational complexity. So, well, naturally, you know, do a question which would arise since I had this glowing introduction. So I must be working on the important problems. Do I work on P versus NP? No, I don't work on this problem. So then it may seem like I'm working on unimportant problems. Well, that's not the case. Okay? So certainly I would like to believe this, but I am not alone. There are several other people who would agree. There are many problems which are not this same problem, P versus NP, but they are important for their own reasons. They are of independent interest, and they also connect back to this problem. So to our understanding of how things are going to build up. So there are many related problems in computational complexity. There are many sub areas, and I have worked in a few of them, few years at a time. Then either I get bored or I get stuck and I move to something else. So some of the sub areas I've looked at: small space computation, algebraic complexity, Boolean function complexity, and the last thing which I've highlighted there, proof complexity. So in fact, this is now a good time to go back to the title slide. So proof complexity, this is what I want to talk about for some time now. So this was a story of how I came to be working to this area. And proof complexity, in fact, is the area that I started working in only in the last 10 years. So it's not even as if as soon as I started research in complexity, I started working in this. It's my most recent research interest, so to say. Okay, so how do we state proofs? So here's a theorem that everybody here knows. There are infinitely many numbers that are prime. How do you prove this? I think most people here will know many proofs of this. Huh? Mariam Mirzakhani knew 4 to 8 proofs of many problems. Many of you will know many proofs of this. So proof 1 would be the sophisticated audience. Why does this need proof? It's completely simple. This is a proof, right? For an audience like this would be acceptable. But maybe the audience is not that sophisticated, and then you would actually have to give a proof. So then you give something like this, and this has just 2 lines, and then it has this, oh, but not, why is it not on the list? I don't understand. Suddenly, if there's a 11th standard kid looking at this saying, I don't see why this is a proof. Then you have to give something even more. So you can see all of these are proofs. All of these are, I think, valid proofs. But valid is in the eyes of the beholder, right? To whom is this a valid proof and to whom is it not? They are all proofs in some way or the other. So the takeaway message from here is that a proof has a very specific goal. When you write down a proof of a statement, you are trying to convince somebody. So the goal of the proof is to convince whoever is that target audience, the reader, the listener, the verifier, whatever. The goal is to convince that audience that the claimed statement is correct, and that the person who is writing down the proof knows why it is correct, has not just mugged it up from somewhere and copied. Usually this is also one aspect. But certainly it must convince the verifier that the reader that the claimed statement is indeed correct. This is what we expect from a proof. And therefore, to say that there is some notion of a formal proof means that we would need some notion of how to formalize what is a reader, who is the verifier. No? Unless we specify that, we can't say what is a valid proof or not. So the level of detail required in the proof, we saw from the example of primes, it's going to depend on the ability of whoever is checking the proof. Sophisticated audience, school children audience, middle college audience, the level of detail in the proof will change. Now, ability itself is a kind of ambiguous word. What do we mean by ability? Ability can refer to many of these things and a combination. So it could refer to the mathematical maturity of the audience. It could refer to the facts that are already known to the proof checker, and this should not be confused with maturity. Somebody can have immense mathematical maturity, but just does not know of a particular result. Once told, may be able to string together things very well. So the available database in the minds of the reader is something that is important. The time available with the checker is also a very important issue. I mean, you could write down a proof which is 100 pages long, and a sophisticated, mathematically mature and reasonably well-known, well-read person may still not have the time to read that proof. So that proof is not going to be useful. So we want to talk about when a proof is useful. Does it have the right amount of detail? We need to keep these things in mind. And we would like to make all these things precise in some way that we can understand. So there's this aspect about modern proofs. So far I've been talking about proofs, and I'm like, the way I've been saying this, you're imagining the proof checker to be a human being. But proof checkers are not always human beings. Many modern proofs are actually checked by computer programs. Some proofs are even generated by programs. But that's a completely different discussion. That's not what I'm talking about. So briefly, we may touch upon this point later. But at this point, I'm just talking about a computer trying to check whether a proof is valid or no. So now if it's the program who is a proof checker, well, the program is written by somebody, the coder. That coder could be a person who has immense mathematical maturity. It could be a person who has a very large database, knowledge base, and the coder may have lots of time. But so that would be the most sophisticated proof checker, so to say. The coder himself or herself may be of this type, but still, finally, the coder is not checking the proof. The program is checking the proof. And so therefore, even such a program written by such a coder would expect that the proof follows a very, very rigidly specified syntax. The coder is super smart, but the program can only look at what is given to it and can only do what it has been told to do. So the proof has to adhere to a very, very rigidly specified syntax. It has to use inference rules. Whenever you're proving something, you're making an argument, you're inferring something from some previously known fact. There are underlying rules which say, okay, it is valid to infer this from this. These inference rules must be completely unambiguous. They must be specified right in the beginning. And maybe there are inference rules which are valid, but which the coder did not put into the program. Now, a proof using that rule, this program is going to mark as wrong. So we have to know, we have to specify right in the beginning what is this database of rules as well. And only then we can go around saying that the proof is going to be checked by this program and is going to be certified by this program. So how do we specify syntax? How do we specify inference rules? We have to use the language of formal logic. In some sense, it is the obvious choice, but according to me, it is also the only choice. There is really no other way in which I can think of that you can really make these things precise. The language of formal logic has to come into formalizing what would be a convincing argument and what is an inference rule that can be used. So let's see some example. So consider statements like this. Statement P, so this P is not to be confused with the polynomial time P. Maybe this was not a good choice here, P. Okay, statement P, predicate P. It rains. Negation P is it does not rain. And Q will play chess, R will go cycling. Maybe there are statements like this. And then let's say that we are told, if it rains, we'll play chess. Then independently, somebody else also tells us it rains. Then as a normal thinking human being, you would put these two together and conclude they are going to play chess. So there is an inference rule behind this. This is something that in day-to-day life, we would use such a rule all the time without even thinking. But when we want to make it precise in the language of logic, well, this is the rule modus ponens, which says that if I know that the statement P implies Q holds, and if I know that P holds, then I know that Q also holds. That's all that has been done here, right? So this is one rule. Here's another rule. If it rains, we'll play chess. If it does not rain, we'll go cycling. From this, you'll conclude that you're going to do one of the two, because either it rains or it does not rain. So this is what could be called a cut rule. If P implies Q and negation P implies R, then I can conclude that either Q or R is going to happen. We have to be a bit careful here. When I say Q or R, I don't mean exactly one of QR. I mean at least one of Q and R will hold. So these are, like I said, day-to-day reasoning rules that we use, but they can be formalized in the language of logic when we say that there are statements which are written as predicates, and then we have these inference rules which allow us to infer new statements. So this was about the inference rules, and this is what I mean when I say we can make inference rules unambiguous and precise. From P and P implies Q, I can imply Q. This is completely precise. From P implies Q, not P implies R, I can conclude Q or R. This is again very precise. What you put in for P, Q, R is now, it's a question of syntax. What kind of statements will I accept as valid statements with which I can reason? So we need to specify what form these statements can take. Okay, so A, B is better than P, Q. I should have used A, B on the previous slide as well. So these A and B in the previous example, they were it rains, we go cycling, things like that. No, they were very simple statements, but they could also be complex statements. So the syntax is just specifying what are the form of simple statements, what are the forms of the allowed combinations. And this is an example which we would use all the time. I may have very simple statements or their negations, and then I just put them together with a disjunction, with an or. C1 or C2 or C3 or P1 or P2. At least one of these must happen. This is a clause. Or it could be, the syntax could say that you're allowed to specify linear inequalities. You're allowed to specify a constraint which says A1 x1 plus A2 x2 plus blah, 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 A and xn is at least T, where all these A's, T, these are all typically integers, whereas the x's, now here I very specifically said they're 0 or 1. I read very recently somewhere that you look at x equals 0 or 1, and then you have to be a mathematical logician or a computer scientist to think that 0, 1 means true, false. I mean, for most other mathematicians, 0, 1, you immediately start thinking of the field or the ring and the additive identity and the multiplicative identity. Computer scientists, this is true and false. So 0 is false, 1 is true most of the time. Okay. So we have placeholders for statements which are true or false. We allow ways of combining the truth or falseness of these statements, and then with those combinations, we can use inference rules to deduce new statements. Okay, good. Some progress we have made. So with this kind of syntax, with these kind of rules, we are going to try and produce proofs which a machine can check. Why are we even bothering to produce machine-checkable proofs? So one could ask this business of machine-checkable proofs or proof checking by computer, is it really here to stay? Should we be investing our effort in trying to formalize these things? Maybe it's just a transient phenomenon. Well, I don't think it's transient at all. In fact, it's going to be more and more inevitable that we will need machine-checkable proofs. Having proofs written in a format that a computer can check, that a program can check, it can help in many ways. For one, it can help in discovering proofs. And I will come to this point a little later. Like I said, proof discovery and proof checking are very different. And the goal of this talk is not so much proof discovery, but some connection, we will come to that. But it can help in automated reasoning and automated theorem proving, in verifying large-scale real-world systems. Are these systems correct? Are they really doing what they are intended to do? This is something which we cannot say is not an important problem. I mean, these are systems which are critical. There are systems which are critical, and we have to have some assurance that they are right. So these are various practical reasons why we would want to look at proof checking by computer. The last one is the computational complexity connection, which is where I came into this, that talking about computerized proof checking and the complexity of that is related to statements in computational complexity, the business of lower bounds. So let's briefly look at some examples which will maybe illustrate this point a little bit more. The planar four-color theorem, I'm sure everybody here is familiar with it. Let me just restate it very, very informally. You have a map drawn on the plane with the regions marked out, and we make some simplifying assumptions that at any one point, only maximum three regions meet. You want to color each region with a color so that adjacent regions get different colors. So it's coloring the countries in a map so that visually you can immediately see this. And the four-color theorem famously says that 4 colors is enough. If the diagram can be drawn on the plane, on a piece of paper, 4 colors is enough. So this was proved in 1976, a humongously long proof. There have been some simpler proofs later, but the simpler proofs are also hard to verify. And it took a long time for the mathematics community to even accept that this has really been proven because of the length of the proof. It was accepted well before 2005, but the 2005 is there, I've highlighted to say that it was those many years later that this proof was finally written in a format which was machine checkable. So it was written in a very, very rigid format. In that format, that proof was arrived at using a general theorem proving software, and then it was verified using this theorem checking software called Coq. Again, the proof was very long. It's not going to become any shorter if you say that you must use a rigid syntax as opposed to you can allow intuitive leaps. So it was probably much longer than the original proof. But now to believe that the proof indeed holds without bugs, you don't need to check the original proof. You don't need to believe the original prover. You need to believe that this proof checker is correct. And the proof checker algorithm itself is short and sweet. So it's a question of moving the trust requirement. Right? Rather than individually checking every line of a very large proof, you individually perhaps check every line of a small proof checking software. So this was done, like I said, for the planar 4-color theorem. For many other theorems, there have been such proofs written. So this is just to make the point that proof discovery and proof checking were very different things. The proof was discovered in 76. The computerized proof checking was done much later. So they're completely different notions. It is not that one automatically implies the other. But on the other hand, here is another problem, the Boolean Pythagorean triples problem. Pythagoras theorem, everybody knows. So here is a very simple to state conjecture. I have the set of natural numbers. I want to color them. I want to just partition the natural numbers into two sets. So maybe I've called them red and green. One set is red, one set is green. Which numbers you put in the red set is entirely up to you. Put them into these two sets in such a way that in any one set you cannot find a Pythagorean triple. So every Pythagorean triple, any triple of the form 3, 4, 5 or whatever, at least one of them is in each part. You have to break every triple. Can you partition the numbers like this? So if you think about this, well, you could ask partition all the natural numbers, or maybe you just can I partition all the numbers up to a certain point? The first 10 numbers, can you partition? Well, the first 10 numbers, there are not those many triples. There's 3, 4, 5. There is so you can very easily do this by hand, and you give me the partition. Then I up the ante. I say, okay, first 100 numbers can you partition? Now there are a few more triples that you have to check, so you explicitly do this. You can still do it. 100 you can do by hand. Then I ask you, how are you going to partition the first 10,000 numbers? Then you will start thinking about what number theory you can use to say that it is some constraints propagate in a nice way, and I need not have to look at all. You could also say, let me try out all possible ways of partitioning, and then this is going to break down very rapidly. 10,000 numbers is too large. And the original statement is about all numbers, no finite bound. Okay, so this is the question. Can we partition all the natural numbers? Can we partition numbers up to a certain point? Up to what point? Up to what point can we prove that it is possible to partition? This problem was solved only in 2016, although there had been people thinking about this problem for several years before that. I mean, it's not a problem that requires sophisticated math to arrive at, right? The statement of the problem is something that, I don't know, it may have been there even in Euclid's time, but maybe they didn't think it interesting enough to work on. So these three people solved it a few years ago. The way they solved it was by writing the statement itself, the statement which we want to try and prove one way or the other, in a suitably chosen logical language. The logical language they used was propositional satisfiability, which I will describe a little bit later. They used computer-assisted proof search. So I was talking about proof checking and proof discovery being two different things. They used proof search on a computer to find. They used it to try and find a partition, to try and rule out partitions both ways. They didn't know the answer, no. So they did use this, but at the end, when they arrived at the answer, they didn't just remember the question was, is it possible to partition the numbers? Let's say up to 10,000. An answer to this would be yes or no. But their program did not finally just spit out an answer yes or no, because if it spits out an answer, why is anybody going to believe them? It had to spit out a proof. And that should have been a proof that others would accept if they wanted any recognition for their work, right? So their program produced a proof which was large, and there was no question of any other human being checking that proof. So they made sure that the proof that they produced was in a machine-checkable format. It's simply completely impossible for a human being to actually check that proof. So let me say something more about this a little later. In particular, you can try and think about where this, at what point the answer to this will kick in. But the point of this slide is to say that this was an excellent example of where proof discovery and proof checking went hand in hand. So it is not that they started off with a proof which had to be checked. They did not know the proof because they did not even know that there is a proof. They did not know the answer to the question. But in order to find that answer, the software they were using, they had to make it smarter and smarter. They had to tinker with the code. So these two very different notions, proof discovery, proof checking, actually they interacted in a very nice way, both improving upon each other in some sense, and eventually they were able to solve this question. We'll come back to this a little later when we formalize a few more things. Yeah. So it will when we formalize this, then we'll come to it. What is Boolean about this? Yeah, very good question. So what is Boolean about this? Boolean, we are talking about two values, 0 and 1. So I want to put the numbers into two sets so that all triples are broken. And now we know the answer to this, which I will come to soon. But you could also ask, can I put the thing into 3 sets? Can I put them into 4 sets? And of course, if you put it into 2 sets, then you can also put it into 3 where the third is empty. So initially it was believed that these questions have different complexity. So the 2-set version is called the Boolean Pythagorean triples problem. Okay, a more practical setting. So I'm just giving examples, right? Planar Fourier theorem, the Boolean Pythagorean triple problem. A more practical setting is verification, where you have a very large system or a program, maybe something which underlies the operation of a nuclear plant, for instance, or a satellite. So now this is a large system. You want to have some confidence that it behaves as it is expected. It should behave like that on long enough runs. It's not like some finite amount of time that it's running, and then after that it can do whatever it wants. So there's some notion of forever, or at least forever for the life of that system, it is behaving in the right way. How are you going to prove a statement like this? I mean, you cannot run it to find out whether it's doing the right thing, because it's a critical thing. If it makes a mistake, then you're doomed. So you formulate the requirements in some sense using logical statements, using logical language, and then the system is good if for every run of the system, there is expected behavior. So the system should satisfy all the constraints. So the requirements, these constraints are logical statements. For all runs, it satisfies all the constraints, then it's good. If there is even one run where a constraint is violated, that's bad. So now you take the logical formulation of this sentence. The system behavior violates some constraint. Okay? This statement, it has an expression in whatever logical formulation you choose, and you prove that it is impossible to satisfy this. This statement is simply unsatisfiable. So if it is unsatisfiable, you cannot make the system behave in such a way that it violates the constraint. That means that it satisfies all the constraints all the time. So this is a situation where you would want to prove in the logical language, whatever statement you have written, you would want to prove that that statement is unsatisfiable. Unsatisfiable is good, and satisfiable is bad. The proof itself, again, it must be convincing. It must be short, it must be checkable. But the proof could be huge because there are just thousands of parameters. We are talking about a system underlying the operation of a satellite, for instance. There are lots and lots of parameters. So this is an example where there is just no alternative to machine checkability. There is no question of sitting and checking unsatisfiability. It's going to be well beyond the lifetime of that satellite and several more satellites to come. So this is the sense in which I'm saying that machine checkability, we cannot think of it as a transient phenomenon. It is here to stay and we have to deal with it. Connections to computational complexity. This was the fourth thing in my point. Why are we bothering with such proofs? Polynomial time, remember I said that this is the class of problems which can be solved efficiently in time. Okay. And there is this class NP, the other class where you can verify solutions quickly. It also has this name, non-deterministic polynomial time, computational problems where yes instances have short proofs. There are problems which are, well, maybe they may not, we don't even know whether they are in NP perhaps, but they can be solved using not too much space. You don't need too much memory or too much disk space, then that's the class P space. And this foundational work that I referred to earlier in the 70s, the P versus NP problem and so on, there were 3 people I mentioned there, but here I've specifically mentioned Steve Cook. He showed that this problem of propositional satisfiability, SAT is NP complete. So this is something very specific about these two classes, P versus NP, and satisfiability is in the class NP, but it is the hardest problem in that class. But if you look at the title of that paper, the complexity of theorem proving procedures. And this is not an accident. I mean, Cook also came to this question from the viewpoint of logic and computation. And so in some sense, what we are looking at, what constitutes a proof, what constitutes a checkable proof, an easily checkable proof, these are not just questions of logic and philosophy, they are questions which are directly related to real world computation. So the paper title I've highlighted here simply for that reason. Okay, so if you're talking about computational complexity, complexity kind of suggests that you are looking at how does the runtime or the space required by an algorithm, how does it scale with input size? You want to invert a matrix, small matrices you can invert fast, larger matrices take longer. How much longer? As a function of the input size. But here we are talking about proving theorems. A theorem is one statement. And by now, if you have seen enough of asymptotic notation, you know that one statement thing is like something that a finite state automaton can do. It's a constant, right? So what do we mean if we say that proof complexity can say anything meaningful about computational complexity? The only way we can make sense of this is by saying that a proof itself should be viewed as a family of statements, not just one statement. Otherwise there is nothing to prove really here. So we must think in terms of classes of statements. For instance, the Boolean Pythagoras triple problem, it was one statement, but you can ask the bounded question, right? Formulate the statement, all triples with numbers less than or equal to m, like up to 10,000, up to 100,000, those can be broken. So now this is a family of statements, right? For every m, there is a statement Sm. I can ask you to prove Sm, and maybe Sm is true and the proof requires large size. Then I can ask, how does the size of the proof grow with m? So now I have this notion of, again, asymptotic size. A theorem, I'm viewing it as a family of statements, and each of these statements presumably can be proven in some way, but the size of the proof is going to depend on which statement in this family you are currently looking at. So we want to ask this question, how does the proof length grow with the theorem size? But really now I've pulled out from theorem many sub-theorems, and they're really all the same statement, but instantiated differently. Okay, so this connection between proof complexity and computational complexity was made actually by Cook and one of his students, Rekha, a little later in the late 70s, the foundations of propositional proof complexity. So remember, problems in NP were the problems I mentioned very loosely. Yes answers, you can provide certificates which can be quickly verified. But there was nothing said about no answers. I mean, this is a problem for which every instance the answer is yes or no. If I say the answer is yes, I can give you a proof and you can check it. If I say the answer is no, I don't know what proof to give that can be checked. Okay? So that's the complement of NP. What I've written here is co-NP. There are no short proofs for no instances known. And to separate NP from co-NP, if I believe that NP and co-NP are actually different, then I would need to show that there is no short proof in any easily checkable format. So this is what brings us back to checking proofs written in specific formats. But here I need any easily checkable format. All that I require is the easily checkable. And once we have come to this notion of computational complexity, we understand what is easily checkable. Easily checkable means a program which runs in time polynomial in the length of its input can check the program. Okay? So our meaning of easily checkable is now polynomial time in this setting. But now we need to show, the lower bound we have, the lower bound requirement, we want to show that there is no short proof in any such format of writing the proof. Any such algorithm which tries to check proofs will take a long time to check this. Will not just take a long time, maybe there is no short proof at all. So, okay. So this is now a very difficult question, and the open question here is to ask, is there an optimal proof format? So the proof format, the format is step back a little bit. We said the syntax of a proof is how do you write down individual statements and how do you combine them. The proof format is what are the rules of inference that you are allowed to use. How do you combine statements and infer new statements. So there is no one format that you need to look at. As long as the format can be checked by a computer reasonably efficiently, we would be fine. So if you look at this lower bound question there, it's asking, are there statements which are hard to prove no matter which format you use? In some sense, it is a little bit like the lower bounds and algorithms question. Are there problems which are hard to solve no matter what algorithm you use? You don't know the algorithm. Lower bounds are against unknown algorithms. So similarly, here we are looking for lower bounds on proof length against unknown formats. But when we look at lower bounds against unknown algorithms, we had one canonical hard problem, SAT, and it was enough to prove lower bounds for SAT. So similarly, one could ask, is there one proof format? And if you give me a lower bound in that proof format, then I know that no other proof format can be efficient. This is still open. We do not know whether there are optimal proofs. I will probably interchange for proof format and proof system. They are the same thing. So we do not know whether optimal proof systems actually exist. So in that sense, the task is now harder because we do not even know for which proof system should we start proving lower bounds. In the context of problems, we know for satisfiability, we should prove the lower bound, or for anything which is equivalent to SAT. But here, we do not know which is the proof format which we should target to get a lower bound. And there may not be one best proof system.
A format in which you write a proof in any other format. In this format, it's not too much longer than
Exactly. So what we mean is that any proof in any other format, in any other checkable format, easily checkable format, can be rewritten as a proof in this format. Yes.
So what if you take a proof written in some format and then to rewrite it in another format, you first
you use a different set of rules.
You prove the set of rules in the new format.
Yes. And then you can freely use them. Yes. That would be allowed.
But can you not do that? Won't it add a constant over it?
Depends on how complex your inference rules are.
Yeah, but that the complexity of that part will depend on the length of the proof that you're.
Not necessarily, but it can, because some inference rules are actually, although we say that these are finite, like for instance, when we are specifying a grammar, there's only a finite set of rules. So similarly, in a proof format, I would have only a finite set of inference rules, but these inference rules may actually each encode an infinite family. So it's a scheme. So I'm saying I have an inference rule of the form A and A implies B gives B. But I have not specified what is A and what is B. And I'm saying that anything of this form can be rewritten like this. So then just to derive this rule from that, it may depend on what you instantiate A and B with. So in some sense, there is a universal quantifier sitting there. I'm saying for every A and every B, A and A implies B gives B. This could be an inference rule. Whereas the first system just had a very specific rule for a specific A and a specific B. So this actually does happen. Modus ponens is a schema. Yes. So there are systems which have individual rules and there are systems which have schemes. And the lower bounds that we are looking for will need schemes. And then translating schemes can become hard. Okay, so like I said here, this question of is there an optimal proof format is something we do not yet know. We have to take steps towards, I mean, just because we don't know how to reach there doesn't mean that we stop where we are. As practice cases, let's specify specific formats and show in those formats at least can we prove lower bounds. So if I give you a specific format for writing a proof, I ask you in this format, can you show that some statement is true, but you cannot prove it easily? Then it tells you that this system is limited. And if I want to use in practice something which checks proofs, I should use a more powerful system. So the lower bound in a particular proof system is helpful in telling me that this system is not enough in practice. I need to add something more. So maybe I have a set of inference rules which can prove everything that I'm interested in, but it takes too long to prove it. I should throw in some more inference rules. That is the message I would take from a statement like this. If I can show that for some if I can show that for some statement in some format there is no short proof, then that tells me that I should extend the format. Okay? So that's why I would try to prove such low. And these kind of lower bounds, many such lower bounds have been proven. So in particular, Oh, I see. Before I move to in particular, one more big question. So I've already mentioned these couple of questions. One is finding lower bounds in specific proof systems, finding an optimal proof format, separating complexity classes. Here's one more question which I'd like to mention briefly before I go to a specific example of a proof format. This is, if potential proofs are very long, then an automated theorem proving procedure, not a proof checking procedure, but a theorem proving procedure which searches for proofs. It will obviously take long. If there are no short proofs at all, then how will this program which tries to search for a proof find one quickly? Even if it gets everything right at first shot, gets the right proof in whatever search mechanism it's trying to search, it will take at least as long as it takes to write down that proof. So no short proofs means theorem proving will take very long. So lower bounds on proof size expose the inherent limitations of, proof search can only go so far. But the related interesting question is that even when there are short proofs, a program which is trying to automate finding a proof may still take long to find it. So maybe there is a statement for which there is a proof with 1,000 lines, and a proof searching procedure which does a brute force search could take like 2 raised to 1,000 time steps to find it. That's too much. So if there are no short proofs, of course this proof searching procedure is doomed. But even when there are short proofs, we do not know whether we can easily find such proofs in an automated way. And this is the question of what is called automatability. Which proof systems are automatable? That is, in which formats, when you write a proof, you know that there is a way of finding a short proof provided it exists. This is again something which is very interesting. In some sense, it seems like a meta question, but again, it is relevant in terms of automated theorem proving. Okay, so maybe now we should move to this specific system, and we have to come back to the Pythagorean triples problem. So the propositional proof systems, which is what Cook and Rekhau talked about, the format of a theorem. How do we specify a theorem? By giving a propositional tautology. What do I mean by a tautology? It's some expression involving Boolean valued variables, involving Boolean connectives and or negation, and it should evaluate to true on every assignment to the variables. Every variable is taking a value 0 or 1, true or false. You plug in the values to all the variables, you evaluate that expression, it should be true. You plug in a different valuation, it should be true all the time. That's what is a propositional tautology. So I could write it this way. F is this formula or expression in terms of x1 to xn, and for every value of x1 to xn, the formula turns out to be true. So instead of saying f is equal to true, I just say f. F means it's true, right? That's what I'm saying. How do we prove that a example is that a formula is a tautology? So here's an example of a tautology: x or negation of x. This right in the beginning, I said it rains or it does not rain. We all accepted that this is a tautology. Here's another example. It's not so obvious that it is a tautology, but with some work, you can like plow your way through and figure out that it is. And if you don't want to, that's also fine. Believe me, this is a tautology. But here is one way in which I can see why it is a tautology. This is a proof by visual depiction. Now, if there were some assignment which made this false, then that assignment had better set x1 to true. Because if x1 were false, automatically this becomes, this is just an OR of many things. It's saying that all of them are true. So if at all there were an assignment which made this false, it must set x1 to true, it must set x2 to true. If it sets x1 and x2 to true, then it would also have to set y1 to false. It would have to set, so I can propagate constraints like this: x1 to true, so y1 will have to be true, y2 will have to be true, and so on. You go up all the way looking at these clauses. Now remember that in the syntax that I mentioned earlier, a clause is an OR of variables or their negations. So all the constraints here are clauses, and I can look at these clauses and combine them in a way to infer more and more things. And eventually I infer that yn will have to be true. But if y1 will have to be true, then the formula is anyway true. So if I try to falsify everything else, then yn ends up being true and the formula is true. Some kind of reasoning went on behind this. I mean, the picture is probably nicer than what I'm saying in words, but this can be formalized. That is the important point. And the way it is formalized, oh, I have written something more there. Ignore that. The way it is formalized is this, the way I will talk about is a system called resolution. So before coming to that, let's see, what did we do in trying to prove that that statement was a tautology? Well, fx is a tautology if for every x it is true. For every x, f of x is true. There does not exist a single x for which fx is false. There does not exist a single x for which not fx is true. If there does not even exist one x for which not fx is true, then it means that not fx is unsatisfiable. So remember, this word unsatisfiable came when we were talking about verification of systems. Unsatisfiability is a good thing. Unsatisfiability of the negated formula is the tautology of the original formula. And so we are going to focus on deciding whether a propositional formula is satisfiable or whether it is not satisfiable. It's likely to be a computationally hard problem, but we can still talk about proof length. And even though satisfiability is such a hard problem, in practice, so there is this disconnect between theory and practice. Theoretical studies so far tell us satisfiability we don't know how to solve. It's NP complete. If you can give me an efficient algorithm and prove that it is correct, you'll get $1 million and you'll get fame and what else. So we don't believe that we can solve it efficiently. But if you ask practitioners in many applications, they are very happy if solving their problem reduces to SAT. In practice, SAT solvers do a fantastic job of solving satisfiability instances with thousands of variables, thousands, maybe even millions. I'm not very sure what is the current benchmark. They do very well. And they do very well simply because they don't have to work against all inputs. They only have to work against inputs which arise in practice. Typically, inputs which arise in practice have structure, and they are able to exploit that structure. So what these solvers actually do, they are given a formula, they are trying to check, is this formula satisfiable or no? They don't know the answer a priori. And at the end, they cannot just give this yes, no answer, no, because nobody is going to believe what that program says. So at the end, what happens is, if the formula is not a tautology, then the run of the solver will give as a witness an assignment which is making it false. Here's why it is not a tautology. Right? That's a proof. Now that proof can be very easily checked. You take that assignment, you plug it into the formula and you evaluate it. Plugging an assignment into a formula and evaluating is a very easy task. Believe me, it's in P, it is in much smaller complexity classes. But when F is indeed a tautology, then it is much harder to prove. How am I going to prove to you that on every single assignment the value is true? How is the program going to prove this? It will have to give some sort of a proof, and that proof is going to come from the trace of what the program did at which step, and that is what we can formalize as a proof system. That's exactly what we are talking about when we say, tell me precisely what are the inference steps that went into this. So coming back to the Pythagorean triple problem. So recall this bounded statement SM. The set 1 to m can be partitioned into two sets, neither of which contains a Pythagorean triple. So this what did these three people who solved this problem do? They wrote it as a propositional satisfiability problem. What was the propositional satisfiability problem? They used Boolean variables xi to denote the partition. Xi is true means the number I goes in the red set. Xi is false means the number I goes in the green set. So true, false values encode red, green. Then they collected clauses expressing constraints for each Pythagorean triple. So if A, B, C formed a triple, A square plus B square equals C square, then you want to say that all three cannot be red. So all three cannot be red is saying that at least one of them should be green, at least either not of XA or not of XB or not of XC. Similarly, all three cannot be green, at least one of them should be red. So for every triple, you just write these two clauses. At least one of them is red, at least one of them is green. And now the statement SM says that there is a way of partitioning the numbers 1 to m so that all these clauses are satisfied. All these clauses meaning there are two clauses per triple. You just collect all those triples into your formula. And now you don't know the answer. You use a SAT solver. We said that SAT solvers do very well in practice in industry applications, but this is not an industry application. This is, some armchair number theorist recreational math going on. It's not clear that this is a structured instance. And sure enough, initially when they use their SAT solvers, they struggle to get answers. They had to make the SAT solvers more efficient, which is why I said this proof discovery and proof checking went hand in hand. So then eventually they got to the stage where up to 7824, they found that it is satisfiable. And at 7825, the solver produced a proof that it is impossible to partition. So the first 7825 numbers cannot be partitioned, and which means, of course, that you take a larger set also, it cannot be partitioned. And at this bound 7825, there are 9472 triples, Pythagorean triples. Each triple is giving rise to two clauses. So we're talking about a set of 20,000 clauses. We're talking of a set of less than 8,000 variables. It doesn't seem that large when I said that industrial level you can solve with millions of variables. But like I said, this was not that structured. So with about 10,000, less than 10,000, 8,000 variables and 20,000 clauses, each clause is quite a small clause with just 3 variables. This solver It took a huge amount of time. It involved a huge amount of compute power. It ran for 30,000 hours on one of the most powerful computers at University of Texas, Austin. It is loosely based on a generalization of this proof system resolution, which I will spend a few minutes on. The proof that the formula finally is unsatisfiable at 7825, it was in a specific format called DRAT, not resolution, but a little bit more generalization. That proof, I mean, like I said, the machine can spit out a proof. That proof can be written down, and that proof is 200 terabytes. So where is the question of a human being checking this proof? I mean, it has to be checked by a computer, right? So the computer program which is going to check this proof, it was a program which could check proofs written in the format of DRAT. And that is why we would be looking for proofs of this one. There was an article in Nature when this was also, this is the picture of the supercomputer on which this Pythagorean triple thing was solved. And the title of this article, 200 terabyte maths proof is largest ever. And this was in 2016. By now, I don't think this is the largest ever. There are these guys and some others have produced larger proofs of other math statements, again, using SAT solvers. This is a pictorial description that one of the authors gave of how to color the numbers. He used red and blue, not red and green. Same thing, no? So he arranged the numbers in a grid in a certain way and said, some of them must be red and some must be blue. And the whites are numbers which it does not matter which side you put them in, they do not affect the satisfiability. Okay, so Boolean Pythagorean triples problem is solved. The answer is no, you cannot partition them into two sets. So now you can go to the non-Boolean case. Can you partition them into three sets and break all triples? We still don't know the answer. So like I said, initially, it was not clear whether all of these are equivalent. The answers to none of them were known. Now we know the answer for two coloring, but we don't know the answer for any larger sets.
Pen which you wrote, does it have a thing for every Pythagorean triple you're adding it? It's not like the Dr. itself is not coded like if ABC satisfy this, then
No. Because checking whether a triple is a Pythagorean triple is something you can do very easily. So for every Pythagorean triple, these clauses were thrown in. Yeah.
How long is FM itself as a statement in terms of M? This could be, okay, it's only n cube long.
It's only n cube long. And actually it probably is much less because many numbers, but it's definitely not. If you have numbers up to n, there are at most n cube triples. Each triple gives rise to two clauses. So you will have order m cube clauses in your statement. So this is something that happens very often when we think of a theorem as a family of theorems, not just as one theorem. Otherwise, complexity makes no sense. And then the size of the nth formula in the family should be polynomial in n. It does not have to be exactly length n, some polynomial in n. And the lower bounds question we are looking for is it the case that there is no proof of length polynomial in n? In this case, the answer is yes, there is no proof of length polynomial in n because there is no proof at all. It is not satisfiable to begin with. But this is the kind of question one could ask. Sorry?
A and B determines
A and B? It's true. Yeah, even better. So the formula becomes smaller. Yeah. Okay, so this resolution proof system, which I mentioned earlier, loosely speaking, that Pythagorean triple SAT solvers, they were based on resolution. They are not quite resolution.
X squared plus y squared is something that is bigger than x.
Again, then you don't have to write anything for it. Yeah. So you want all three numbers to be less than it. Yeah. So all those pruning hacks they did. And it was still too much for the existing solvers. So they had to tinker with the solvers and they did something that they call a cube and conquer method, which they built into their solver. So there, of the three of them, I think one of them is an out and out mathematician and two of them are these amazing combination of theoretical computer science, mathematics and hands-on coding, engineering level coding. Yeah, so this resolution proof system is a particular proof system or a particular proof format in which you can show that statements are false or their negations or tautologies. So it's the most widely used propositional proof system, and most SAT solvers that are currently so successful are loosely based on resolution. Not just resolution, they use a little bit of generalizations beyond that, but the basic underlying theme is resolution. And resolution itself is an extremely simple proof system. In this proof system, the theorem should be encoded like this as a set of clauses. the example which I showed you earlier and I gave a visual depiction. There's a bunch of constraints. Each constraint involves some of the variables, but the constraint only says that at least one of these must be true. It's just a pure OR of variables or the negations. And then you have the conjunction of, satisfy all the constraints. So this is the format for the theorem. What is the inference rule? There is just one inference rule, which we saw right in the beginning, the cut rule. An assignment which satisfies a bunch of clauses. And in that bunch of clauses, you have A or X, you also have B or not X. That same assignment has to satisfy A or B. Because in that assignment, X is either true or false. If X is true, then how did it satisfy B or not X? Not because of the X part. So it's obviously satisfying B. And if X were false, how did it satisfy this? Obviously because of the A part. So any assignment satisfying both of these must satisfy A or B. So I just have this one inference rule. So I start off with a bag of clauses, and then I keep searching in my bag. If there are two clauses which syntactically look like this, A or X, B or not X, then I can throw in A or B. The bag becomes bigger. But when does this process stop? I keep on adding more and more clauses to my bag. At some point, of course, you can't add any more clauses because there's only a finite number of clauses on these variables. But I want to stop when it is clear to me that this formula is not satisfiable. And that is going to become clear if finally I can add to the bag the empty clause. There is no assignment which satisfies the empty clause. To make a clause true, you have to make something in it true. If there is nothing in it, how can you make it true, right? So the goal is to produce the empty clause. See, in this example, the clauses in green boxes are what are the initial bag. These are the clauses which are given. And now I'm using the resolution rule. If I know that x2 has to be true and not y1, not x2, y2 has to be true, then it must be the case that not y1 or y. It's just syntactically applying that resolution rule. So I can syntactically apply resolution here, 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 and proceed like this. And then but on the one side, I'm concluding that y3 must be true. On the other side, I'm told that y3 must be false. This is impossible. So once I finally reach the empty clause, I know that the formula was unsatisfiable to begin with. This is a proof of unsatisfiability, which is qualitatively, you can see, very different from saying try out all assignments and check that they are all false. I have not tried out all assignments. But if you follow the logical reasoning, you are convinced. Because you just check every derivation step. Yes, is this a valid application of resolution? Is this a valid application of... You check every step is a valid application of resolution to clauses which were already derived. And finally, you got the empty clause. Okay, you believe me. So this is how the inference rules have been used in a sequence of steps to finally convince whoever is the reader or the verifier that this formula is unsatisfiable. The length of the proof, the number of times you have to use a resolution step. So now that is what we are going to look at. What is the length of the proof? What can you do easily in resolution? For instance, if I have this kind of directed acyclic graph, that's why I drew that visualization picture. And I have a variable for every node. And I have clauses which say that at the source nodes, it must be true. At the sink node, it must be false. And at every intermediate node, if what comes in from everywhere is true, then this must also be true. Then you can see that there is something wrong in this, right? You're starting off with true. Trues can only propagate trues, but at the end you will reach a false. How can that be possible? Code this explicitly using these clauses, and with resolution you can actually prove that indeed there is a contradiction there. And the size of the formula, initial formula, is proportional to the size of the graph. The size of the resolution proof is also proportional to the size of the graph. So it's a short, small proof. So this is something that resolution can do easily. Here is something that resolution cannot do easily, and it is an equally simple and easy to see statement, the pigeonhole principle. N plus 1 pigeons have to go into n holes. Can it be that every hole has only one pigeon? Some hole must have two pigeons. You encode this using propositional satisfiability. So you'll have to write down the clauses. Typically, in most encodings that I have seen, there would be variables of the form xij. Ith pigeon goes into jth hole. And then eventually you can derive a contradiction. So if you write down the right clauses for n plus 1 pigeons and n holes, there will be roughly n cube clauses, or n square or n cube. N cube. The encoding I have in mind is roughly n cube. And you can prove that if resolution is the only inference rule you are allowed, then you will need 2 raised to n steps to reach the contradiction. It's completely obvious to us when we say this in English language and we think through it that this statement is false. but the program which is checking this does not know this, does not have this intuition. It's going to blindly check step by step, has resolution been applied correctly, and any such proof which only applies resolution and nothing else is going to require exponentially many steps.
But the fact that PhD requires under the to use it is like
Does it itself use the pigeonhole principle? Probably does. Yes, because that is one of our bread and butter techniques. Yeah, yeah, it's a nice combinatorial argument, and yeah, it would use the pigeonhole, not in this vanilla form, maybe in a slightly more general form. Yeah.
Is there any other format that is ordered?
Oh, there are many. Yes, yes. In particular, there is a right in the beginning when I was talking about formats and syntax, I mentioned linear inequalities. So there is another proof system called cutting planes, which works with inequalities. So you encode the same initial constraints, not as logical clauses, but as integer inequalities, and then it has very short proofs. There are also algebraic proof systems, where you encode true and false as polynomial equations, not as logical clauses. But so the encoding is up to you, as long as you specify clearly what it is, right? So there are algebraic systems where you can write down a bunch of polynomial equations, one for every initial constraint, and then you want to find an assignment which satisfies all the equations. And you are allowed certain rules for how to combine polynomials. And in those systems, again, cutting planes is easy. So there are many formats in which it is used. Some other things which are hard for resolution, there's this mutilated chessboard problem. You take a chessboard and you knock off opposite corners, and the opposite corners are both the same color. So you take off two whites and then you say, can you cover this by a 2x1 tiling? You can't do that. And this is again completely obvious to most of us, although this is not as obvious as pigeonhole. This is not something that is going to be obvious to a 4th standard kid. Whereas pigeonhole, I think you can explain to a kid in 4th standard in school. So it's not that obvious, but it is still not very complicated. And resolution struggles with this exponential size. There's another formula. Let's not even get into that. We're out of time. A few minutes more, I want to just very briefly mention what happens beyond SAT. Few minutes more is okay? Okay. So inspired by the success of resolution-based SAT solving, I did mention places where SAT struggles. It does not, resolution struggles. Resolution cannot count. It cannot figure out that there are n+1 pigeons and n holes. This is often worded as resolution cannot count. Okay. But despite that, in practice, resolution-based solvers with a few additional tricks with some pre-processing thrown in, they do quite well. And so from the practitioner's point of view, as opposed to from the theory point of view, there's very good reason to say, okay, SAT is done. So let's go beyond SAT. What more can we solve? And what more can we solve? Okay, here's propositional tautologies, which are just saying, for every valuation of X, this formula is true. I could add to the complexity by mixing for all and there exists. So I could have something like this. There exists an X such that for every Y, the inner product of X and Y is even. So X is actually a vector of variables, X1 to Xn, Y is a vector of variables. For there exists an X such that no matter what Y you give to it, the inner product XY is an even number. This is a true statement. I mean, the X can be 0, and then no matter what Y you give to it, the inner product of X and Y is 0, which is even. I could also write there exists an X such that for every Y, XY is odd. And this is obviously false, because when Y is 0, the inner product is always 0, which is an even number. So I could now start mixing up for all there exists and in various different ways. And you can see that in some sense, deciding whether the statement is true or false is going to become more complex. It's not more expressive than propositional tautologies. By using quantifiers like this, it's not that I can say more things than what I could say earlier, but I can say things more compactly. I don't have to write down very long statements. Okay? So by allowing a mix of existential and for all quantifiers, I can say things more compactly. Saying things more compactly means the potential theorem that you are trying to prove, instead of being 1000 bits long, is now 90 bits long. And now I want to prove which is polynomial in this size, not in that size. No? So stating the theorem more compactly is good if you are trying to memorize that theorem. But if you are trying to look at how long is the proof, the shorter the theorem, the longer the proof relative to the size of the theorem. So Now let's see, what can you do with these kind of quantifiers? So actually NP, in some sense, it codes what happens in a one-player game. Minesweepers, Sudoku, there are many other one-player games. There's a whole, I shouldn't say laundry list, but there's a huge compendium of combinatorial puzzles and games where deciding whether there is a solution or no is known to be NP complete. Okay. But P-space is the potentially larger complexity class, and it moves over from one-player games to two-player games. There are two people who are playing, and you want to know which of them can always force a win, no matter how the other person plays. Tic-tac-toe is the simplest example. Chess, Go, Antakshari. Antakshari you can think of as a two-player game with a fixed database. All the songs must come from this set. And now, depending on the person who starts, who is it who can force a win? So the question we are asking is not satisfiability. The question we are asking is who can force a win? And we can, as before, set up an appropriate encoding, encode the game as a Boolean formula with, now you will have existential and universal quantifiers. You can fix a proof format. So the formula we have got now is a quantified Boolean formula. So that's this QBF. And then we are asking the same question that we asked earlier for propositional tautologies. When is this formula hard to refute? Which kind of formulas are hard to refute? That's QBF proof complexity. So this is the area that I work in now, and I was introduced to this area by my friend and collaborator Olaf, who's at Jena. And I think I won't spend too much time on this. Let me just go past this to say, let's see, the two-player game, an example. Yeah, here's an example of a QBF. So I think many of you would not have seen QBFs before, so maybe just a couple of minutes to stare at this to get a feel for what I mean when I say. So here is a quantified Boolean formula. I've called it equality n. There exists x1, x2 up to xn. So these are all there exists, such that for every u1 to un, there exists a t1 to tn, such that all these clauses inside are satisfied. What are all these clauses? For every n, there is a for every I in n, there is a clause of the form xi or ui or ti. For every I in n, there is a clause of the form xi bar or ui bar or ti. And then there is one more clause which says that at least one of the t variables must be false. T1 bar or T2 bar. I've written it as a set because I didn't want to keep writing or. So now, what do I mean when I say this is a two-player game? There are variables of two types, right? Existential and universal. So there are two players. There's an existential player who gives the values of the red variables. There's the universal player who gives the values of the blue variables, but they have to give the variables in that order. So the red player starts first and says, okay, I'm going to set x1, x2, x3 to be 0, 0, 1. Then the blue player has to respond. Blue player says, okay, I'm going to set u to be 0, 1, 1. Now it's the red player's turn. The red player responds with 1, 0, 1. Now you have values for all the variables. You plug it in and you check, oh, all the clauses are satisfied. The red player wins. Another run could be like this. The red player again starts with 0, 0, 1. The blue player starts with responds with 0, 0, 1. The red player responds in this way, and now there's one clause which is falsified. The universal player wins. So these two runs that I have shown here, sometimes this guy is winning, sometimes that guy is winning. Actually, it turns out that one of the two players can always force a win. One of the two players can always, there is a way of playing really smartly so that no matter how the other person plays, this player will win. In this example, can you see who can win? I'll wait for 10 seconds. You don't have to see it by then, I'll tell you then. So here the question is not about whether the player who starts can win, because who starts and who ends, it depends entirely on the order in which we write the variables in the beginning. Right? There is no choice. Okay, in this example, I claim that the universal player can always win. The blue player. The blue player is just going to say that every u is the same as x. If every u is the same as x, you see what happens to these clauses? You can just completely drop the u. No, it takes the same value as x. So then what are these two clauses in a pair for I? Xi or Ti, Xi bar or Ti. Basically, it's saying that you have to set Ti to true, otherwise you will lose one of those clauses. And if you have to set all the Ti's to true, then you will lose the last clause. So if the universal player plays smartly, then no matter what the existential player does, the universal player can win. And the general question now is this: given a QBF of this form, decide who can win. Prove that indeed that person can win. So we want to prove that QBFs are false, which means we want to prove that the universal player can always win, and we can still use resolution, but it's not going to be enough to finally make the falseness obvious. Resolution alone will not be enough. We'll have to do some other stuff, extend it. So QBF proof systems are often more complicated than propositional proof systems. They have to add other stuff on top of resolution. Why are these proof systems at all? There are two things that we have to keep in mind for a proof system. It should be complete. Whenever a statement is actually true, it should be possible to prove it there. So if I give you a QBF which is actually false, then in your proof system, or by proof system I mean proof format, I mean the collection of inference rules, it should be possible using those rules to prove this fact. Only then the system is complete. And this can be done by mimicking the winning strategy to construct the proof. Proof system should also be sound. It should not be the case that a statement is not true and you end up giving a proof of it. Right? So for that, you would typically take a proof and then extract from it a winning strategy for the universal player to demonstrate that the other player could not have won. So a lot of niceties going on there, and this is work that I have been doing in the last 6-7 years, trying to understand different kinds of QBF proof systems, trying to understand which propositional proof system lower bound techniques can be transferred to QBF. Not all can be transferred. Some can, some need significant adapting. We are looking at different formats and comparing their strengths and so on. So this is the kind of work that I've been doing with various collaborators whom I've mentioned here. So I think this is a good point at which I should stop. Here is, I mean, it's been quite a long talk, but a short summary, a take-home message. Formal proofs, we are measuring how complex, we are trying to measure how complex a proof needs to be. The choice of the language for specifying the theorem as well as the proof matters. The syntax of the proof matters. The choice of the inference rules matters. Proof complexity is aiming to understand the limitations of various formats of, as a side bonus, if we also separate complexity classes, that will be great. But personally, I don't think that's going to happen. Okay. SAT solvers are very useful. They can be even used to prove theorems. So we want to understand them better and understand why they are doing so well, and there they can still be improved. QBF solvers, there is still a long way to go. It's a relatively newer field, which is good news for me as a researcher. A younger field, there are more problems to attack. Right? The answers are not yet known. Okay, so on this note, let me stop now, and I'm happy to answer any questions.
One slide where to show that something is not in tautology or is a tautology, there was this like this Q binary tree. So is there like some have people looked at it, so that reminds you of a circuit? So is
Yes.
there like connection between circuit complexity?
Oh yes. So okay. So the question is there a connection between formulas or circuits for computing and proofs? There is a very close connection. So a lot of lower bounds could be seen as transferring circuit lower bounds or formula lower bounds, but there are lower bounds also in settings, proof lower bounds in settings where there is no corresponding circuit lower bound. So far, it's been largely a one-way connection. In the very recent past, in the last 2-3 years, we have seen results in the other direction, transferring proof lower bounds to circuit lower bounds. Some such results have also been shown in the recent past.
That, for example, if you add another layer of quantifier, it helps you just say things in a compact way. But because you could just, if you didn't have like an existential, you can just do this or something like that. But let's say we want to say statements not just about the about Boolean space, but let's say about we want to say for any polynomial there exists over complex numbers there exists. Let's say we want to try and have a proof for this, then I mean how do proof systems work?
Okay. So the question is about non-Boolean valued statements. So in fact, algebraic proof systems are able to handle statements about polynomials. And I said that we can use polynomials or polynomial equations specifically to encode true or false. But you don't have to think of it that way. So maybe I can just give you a bunch of polynomial equations and I ask you whether they have a common root. Now, these polynomials may not be encoding clauses at all. And the algebraic proof systems have mechanisms to prove precisely this, the non-existence of a common root. So if a bunch of polynomial equations, P1 equals 0, P2 equals 0, and so on, Pn equals 0, if they don't have a common root, a little bit like Euclid's algorithm, you can actually find multipliers for these polynomials. And when you take f1 P1 plus f2 P2, you get 1. So those f1 to fn form a proof. But how quickly can you find those FIs? How efficiently can you construct those FIs? Those are the questions that we would ask as complexity questions in an algebraic proof system.
I have a question related to actually two questions, both of which go hand in hand. So this is regarding the Boolean Pythagorean problem. So this was the first proof of this statement. Do we now know of another proof, or this is
No,
proof?
no, we still don't know of any other proof. The number of terabytes has decreased a bit. From 200 terabytes, I think now there is a proof which may be 56 terabytes or something like that. Because the SAT solver became more efficient. By a factor of 3, from 200 we came to 54, but it's still in that league.
Other math statements for which we knew of proofs, did this method actually give you cleaner proofs than what was known as the
Yeah, so I mean that is a very
cleaner means?
whatever cleaner. So this is a very interesting question. Maybe you have a hugely complex proof which mathematicians have come up with, and by using this automated theorem proving, in some sense, can you come up with a cleaner proof? In fact, very often I think that things go in the other direction, that a proof is discovered through an automated process, and then the mathematicians say, okay, we will use our intuition to come up with a cleaner proof. So in the forward direction, I do not know of any cleaner proof. I thought that the planar 4-color theorem would fit this, but it's not clear that the proof which is verified in Coq is any cleaner. All we know is that it is machine checkable, whereas the original proof was not machine checkable. So if machine checkable with a very small checking code is cleaner, then yes. But I mean, I wouldn't buy that. Yeah.
That sometimes the statement expressed in a different system allows for simpler proofs. So does it not then imply that the soundness of the second system, when encoded, cannot be proved easily in the first system? Because you could always have somehow change. First, you prove that the other system is sound, and then provide the proof in the other system.
I think this is related to what Swagata was asking. So in fact, there is something even more weird going on there, that in a proof system, can you show that this proof system itself is sound? So I mentioned one result about automatability, right? Whenever there are short proofs, can you find short proofs? So this you would want to know for multiple formats. In particular, let's look at this format resolution, which is so simple, so easy to understand. It has just one rule. And now, as of 2 years ago, we have a proof that resolution is not automatable. And how is that proven essentially? It's proven in the following way. It says there exists they come up with a formula which looks like this, which logically says the following. There exists a formula. This there exists is inside the formula. So the variables which encode what goes into a clause. There exists a formula for which there exists a satisfiable assignment, and there exists a proof in resolution. Now we know that resolution is sound, so these two together cannot happen. So therefore, this formula is unsatisfiable. And then they show that proving that this formula is unsatisfiable requires super polynomial size. So in some sense, this is actually proving the soundness of resolution within resolution, right? That it cannot be that for a satisfiable formula, you had a resolution proof. Resolution struggles to do that. And I think almost all the propositional systems that I think have lent themselves to practical implementations. By now, we know that all of them automatability is hard, and it is proven using the same kind of principle. That proving the unsatisfiability of there is a formula which is satisfiable and which has a refutation. This is hard. Whereas the question you are asking is, can I prove the soundness of this in a stronger system? And that often you can do. Similar to? Yes, but that applies to much stronger systems, and now here we're talking about very weak systems. Yes, so it's of the same flavor. Yes.
Going back to my question, so it's not, because in some cases actually computer searches have actually led to cleaner proofs in our sense of the word, whatever that means. I don't know how to formally define. For example, just in search of NP completeness reductions, you want to find the best gadget reduction from problem A to problem B. And once you see a gadget, you realize, oh, this is a nice gadget. But there have been cases in which actually to find the best gadget reduction, they've actually run
Yes.
code, found it out, and then realized, oh my goodness, I should have recognized this as a good gadget in the very beginning. So this has happened back and forth.
Yeah, so this is this interaction between proof discovery and proof search.
So such a similar phenomenon hasn't happened here, where they actually come up with a proof this way and then realize, oh, this proof is actually this clean proof.
Yeah, I do not know of any. So for instance, after the Boolean Pythagorean triple problem, which like I said, may be considered as a recreational math problem, but then after that, two of these authors and somebody else, they proved something about Schur polynomial, or so I don't remember what the statement is because I don't even understand it well enough, but it was something that mathematicians had looked at for long enough. It was interesting, and they still don't have a pure math intuitive proof of it. They only have this computer checkable proof. So I do not know too many examples like this which have been proved only using computers.
Any other questions? Thanks, Meena, again. Conclude today and meet again tomorrow morning.